Hello everybody. I'm going to talk about stress in this lesson. You may have learned about the topic in some other courses. I will treat the topic at a somehow more advanced level that is necessary for this course. I will introduce some new terms and concepts to prepare you for this course. Stress is defined as force divided by area. Stress arises in an object to balance the forces. The third law of Newtonian mechanics dictates that in static equilibrium, forces must be balanced in every direction and in every part. Consider a cylindrical sample of any solid, a column of granite if you like. Subject the column of granite to extensional forces. The external forces must be balanced, of course. Force must be balanced for every part. Imagine that the column is made of an upper part A and a bottom part B divided by a horizontal surface. And consider the interaction between part A and part B through the contact. Now, force balance of part A means that the F pulling it up from the top end must be balanced by a force pulling it down at the contact. Likewise, B must be pulled up at the contact to balance the force pulling it down at its bottom base. So A and B attract each other through this contact. See, the attraction is precisely the same magnitude as the external load. So the total force distributed over a cross-section area of A. That is the origin of the tensile stress on that contact. Stress must be generated in this object to balance the forces, but exactly by what mechanism? The mechanism for stress origin is through electromagnetic interactions among material particles. On the atomic scale, the interatomic force is related to the spacing of interatomic particles. Vertical axis here, interatomic force. Horizontal axis, spacing between interatomic particles. And the interatomic force is something like this curve. For any given material, there is a characteristic equilibrium spacing between neighboring particles, capital D here. If the neighboring particles are forced to move farther than D, then attractive forces develop between them. If the neighboring particles are forced to move closer than D, then repulsive force develops between them. So this is the origin of attractive and repulsive forces. This force is electromagnetic in nature. As long as the change in spacing, small d, is small with respect to the characteristic equilibrium spacing, capital D, then the behavior is elastic. So the stress is actually linearly dependent on this ratio, which is the concept of strength that we will talk about later on. And this linear relationship is Hooke's law. So Hooke's law will hold. So this is the mechanism for stress origin. Let us now move on to analyze the simple situation of a stress state in Earth's crust. That is, the stress state in Earth's crust in equilibrium with gravity, and there are no other forces acting. That stress state is what we call lithostatic stress. The lithostatic stress asks the question, what's the vertical stress acting on a horizontal plane at depth Z? Consider a vertical column of rock with base area delta A. The total force acting on a horizontal area at depth Z is really the total gravity of the overburden rock. That volume of column is base area multiply the depth Z, delta A multiply Z. total mass of this column above this area is the total volume multiply the average density rule. That's this expression. Gravity, to the gravitational force of this column of rock, is going to be the mass multiply the acceleration due to gravity. So the force is this expression. Total gravity is supported by this area. Force divided by the area gives the vertical stress on that area. It's a rho gz. So the vertical stress on a horizontal plane at depth z is this relationship. If we plug in some numbers, so the average density of the continental crust is 2,700 kilograms per cubic meters and g is 9.8 meter per second, we get something like 27 megapascal every kilometer we go down from the surface of the Earth. The stress on a dipping plane is different. First, the area on a dipping plane is no longer delta A, but delta A divided by cosine theta. Theta is the dip angle of the plane. Second, the total vertical force now has a plane normal component, Fn, and plane parallel component, Fs. The plane normal component leads to normal stress. The plane parallel component leads to shear stress. So the total stress on the plane element is a vector called traction, T. T is the total force, which is a vector divided by the area. So we can carry out the analysis similar to the previous slide. The total force is rho gz delta A, the same as the previous slide. The total area now is updated by this A. So total force divided by the area gives this. That's the traction. The magnitude of the traction is rho gz cosine theta. So the normal stress, the stress that is perpendicular to the plane, is the total traction multiplied cosine theta. So it becomes rho gz cosine theta squared. And the shear stress is T sine theta, and it becomes rho gz sine theta cosine theta. From this simple analysis, it is clear that the traction on the area element depends on the orientation of the plane, depends on the dip here. Because the traction depends on the orientation of the plane, there is not a unique traction at a point. Therefore, stress at a point cannot be defined by a traction. To completely define the stress at a point in space in a 3D material, we need to use a coordinate system, x1, x2, x3. We use Cartesian coordinate system for simplicity in this course. Once we have a coordinate system, we need to consider tractions on all three coordinate planes. So the plane perpendicular to x1, the plane perpendicular to x2, and plane perpendicular to x3. We need to know the tractions on each of those three planes in order to fully specify the stress at a point. Since each traction is a vector, it has three Cartesian components. So three tractions will have a total of 9 Cartesian components. If we know the stress matrix, we will be able to calculate the stress on any oriented plane. The stress components will be dependent on the coordinate system that is used. However, because stress is a tensor, stress components in one coordinate system can be transformed to components in another coordinate system using the tensor transformation rule. Stress tensor is also symmetric, which means sigma ij equals sigma ji. So sigma 1, 2 will equal sigma 2, 1. Because of this, the stress matrix has actually only 6 independent components. There is a unique Cartesian coordinate system in which the stress matrix becomes diagonal, and the diagonal stresses are called principal stresses. And the coordinate axes for that unique Cartesian system are called principal stress axes. To calculate the principal stresses and principal stress axes, all we need to do is to take the eigenvalues and eigenvectors of the stress matrix, which is easily done using a mathematical application like MATLAB. While stress has 9 components, 6 independent components, how do we compare two stresses? We use stress invariants. Invariants are scalars that do not depend on coordinate systems. Regardless of the coordinate system you use, the following quantities do not change, and they are stress invariants. There are 3 independent invariants for the stress tensor. One is sigma kk, which is the mean stress that I'm going to talk about later on. Second is a measure of how strong the stress is, and the third one is the determinant of the stress. So here I need to remind you of the Einstein summation convention that we have been using and will be using in this course. By this convention, a repeated index implies summation with respect to the index over the range of 1 to 3. What that means is, if I write down sigma kk, look, this index is repeated. It means the summation of sigma 11, sigma 22, sigma 33. You should imagine that there is a summation sign here. Here in this expression, sigma ij, it doesn't mean just one term. I is repeated. So there is a summation with respect to I. J is repeated. There is a summation with respect to j. Earlier on, I have been using this, the traction on a general plane equal to sigma ik nk. This explicitly is a summation with respect to k, because k is repeated. The total stress tensor is called a couch stress tensor. The diagonal term, sigma 11, 22, 33 averaged, it's called the mean stress. So mean stress is really the first invariant divided by 3. Couch stress, subtract the mean stress. The remaining is called deviatoric stress. You can regard the total couch stress as a mean stress part plus the deviatoric stress part. The reason we make this decomposition is because the mean stress has things to do with volume change. So the mean stress only causes volume expansion or volume reduction. It's the deviatoric stress that is responsible for the shape change of the object. So shear strength is due to deviatoric stress. In the situation of a deviatoric stress, to compare two deviatoric stresses, most useful quantity is the second invariant. Second invariant for the deviatoric stress is this one. Again, we are adopting the Einstein summation convention. The second invariant is a measure of the effective shear stress. In many textbooks, they call this effective shear stress, which is the second invariant of the deviatoric stress square rooted. In many geoscience literature, differential stress is used as a measure of the stress magnitude. The reason we are able to do that is because of the spatial setup of those experiments. In those experiments, the deformation is uniaxial. So the stress state is something like this. The principal stress is acted in the direction of the sample axis, either compression or extension. Sigma 2 and sigma 3 are equal. They are equal to the surrounding pressure. So in this situation, the stress magnitude, sigma 1, subtract sigma 3, the difference in principal stress, called differential stress, is equivalent to the effective stress or the second invariant of the deviatoric stress. But in general, if the stress is truly triaxial, so sigma 1 is not equal to sigma 2 and not equal to sigma 3, then a single differential stress cannot be a measure of the effective shear stress. Force must be balanced in every direction and in every part. That means that the stress cannot vary arbitrarily in a continuous body. To satisfy force balance, stress variation in an object must always follow the following equation if the object is at static equilibrium state. So it's this differential equation. Fi here are components of body force. Body force are force like gravity, buoyancy. So body force acts upon every part of the object. Sometimes we use a shorthand to write this equilibrium equation. This equilibrium equation is derived in many textbooks. If you want to have the details how this equation is derived from Newtonian mechanics, this textbook you can check, Ranani 1995. It's often written in a shorthand form using Einstein convention, so sigma ij, comma, I plus fj equals 0. Here it's using not only the summation convention but also a convention here. A comma means derivative. A, comma, I means derivative of A with respect to spatial coordinate xi. So, this shorthand represents these three equations. We do not specifically solve the equation in this course, however the concept of this is used throughout elastic and viscous problems. The stress state in Earth's lithosphere is very variable, depending on a lot of conditions. Geologists and geodynamists speak of Andersonian stress as a reference. Andersonian stress state may be a good approximation for the upper crust or the brittle lithosphere. Andersonian stress state is such a state where the vertical stress equals the lithostatic value, and the vertical stress is one of the principal stresses. In an Andersonian stress state, there's no shear stress on a horizontal plane, of course. Because the vertical stress is a principal stress, the other two principal stresses must be horizontal. The larger one is called sigma capital H, and the smaller one is sigma lowercase h. Depending on the relative magnitude of these three principal stresses, people speak of normal fault regime, thrust fault regime, and strike slip regime. If the vertical stress is the maximum principal stress, we're dealing with normal fault regime. If the vertical stress is the minimum principal stress, then we're dealing with a thrust regime. If the vertical axis is the intermediate principal stress, then we're dealing with strike slip or wrenching fault regimes. Before I conclude this lesson, I want to have just a few words on sign conventions. In mechanics literature and material science literature, tensile stress is taken positive. In structural geology, tectonics, and geodynamics sometimes, compressive stress is often taken positive. The reason geologists use this convention is because stress in Earth's lithosphere is mostly compressive. However, a lot of mathematical equations and numeric codes for deformation have been developed in the mechanics and the materials science literature. To use the mathematical equations and numerical codes developed in the mechanics and the materials science literature, tensile stress positive convention needs to be used, and that is what we are doing in this course, except in special cases. That's it for this lesson. Thank you for your attention.